There's a comforting assumption hiding inside almost every piece of software we build. The assumption is that there is a single shared present moment. When one service asks another service a question, both of them are imagined to be standing in the same instant of time, looking at the same reality. In a distributed system, that assumption is false. There is no universal now. Each service lives inside its own pocket of time, assembled entirely from the events it happens to have read so far. One service might believe it is 3 in the afternoon. The service it is talking to might still be living in the late morning, simply because it has not yet caught up on the messages in between. We tend to imagine these systems as a single organism with one clock at its heart. They are closer to a scattered collection of observers, each holding a slightly different stopwatch, each convinced that its own time is the real one. This is the idea of the time bubble. Once you see it clearly, a whole category of mysterious, intermittent bugs stops looking like bad luck and starts looking inevitable. To understand why these bubbles form, we need to separate two ideas that usually get collapsed into one word: time. The first is wall clock time. This is the time a service can read off its own machine, the ordinary calendar time ticking forward in the background. The second is event time. This is the time encoded inside the messages a service consumes, the timestamp stamped on each event when it was first produced upstream. A service can always see the wall clock, but its understanding of the world is not built from the wall clock. It is built from event time. Its internal sense of where we are is synchronized to the union of all the event streams it has read, up to the latest offset it has processed in each one. Picture a service reading from a stream of messages. Each message carries a position, an offset, marking how far along the stream it sits. When the service has consumed up to offset 900, its internal picture of reality is the picture painted by those first 900 events and nothing more. Events 901 onward have not entered its world yet. As far as that service is concerned, they have not happened. This is what we mean by a bubble. The boundary of the bubble is the set of offsets the service has reached. Inside the boundary, the service has a complete and self-consistent view. Outside it, there is information that exists in the wider system but has not yet arrived. The service is not wrong about its own state. It is simply current as of a particular point in each of its inputs, and that point may sit far behind the newest events waiting in the streams. Now we can describe exactly how things go wrong. The trouble begins the moment one bubble tries to compare itself to another. Suppose a service has processed events up to an event time of 900. It feels caught up. Then it makes a synchronous call to a second service and asks a direct question. Do you have the record for this particular key? The second service is lagging. It has only processed its stream up to an event time of 220. From its point of view, the record being asked about does not exist yet because the event that would create it is still sitting unread in the stream. The first service receives a confident answer of not found. It treats that answer as truth. But the answer was never about whether the record exists in the system. It was only about whether the record had reached the second service's bubble. Two services in two different moments of time held a conversation as if they shared one moment, and the mismatch produced an error that looks, from the outside, like a genuine bug. This is the synchronous comparison trap, and it is the root of a surprising amount of distributed pain. It helps to name where the lag comes from, because there are two distinct causes that look identical from a distance. The first is service lag. The consumer is healthy but slow. Events are arriving faster than it can process them, so it falls steadily behind. The second is data product lag. Here the consumer is perfectly caught up, but the upstream producer has failed to write the events, or the stream feeding it has gone quiet. The bubble is small not because the reader is slow, but because the world it is reading from has stopped filling in. On top of all this sits clock skew. The clocks across a distributed system are rarely in perfect agreement. Network jitter and intermittent failures mean events can be published slightly out of temporal order, so even the timestamps themselves carry a small dishonesty. The picture each bubble holds is assembled from inputs that may disagree with each other about exactly when things occurred. Here's the part that reframes the whole problem. The instinct, when you first meet these inconsistencies, is to treat them as a failure to fix. Something is broken, and the goal is to force every service into the same instant so the disagreements disappear. But the disagreements are not the malfunction. They are the normal resting state of any system built from independent streams. Asynchronicity is not the exception to chase away. It is the default condition, and the brief moments of perfect agreement are the special case. This flips the usual mental model on its head. A team will often reach for a synchronous API call precisely because it feels safe and immediate, as though asking directly gives a more honest answer than waiting for events to flow. The opposite is true. A cross-service synchronous query is the very thing that drags two unsynchronized bubbles into a single conversation and forces them to pretend they agree. The deeper realization is about what consistency even means here. A system of this kind is called convergent. If, once all the messages in flight have finally been delivered, every replica agrees on the set of stored values. Notice what that definition does not promise. It says nothing about agreement at any particular instant along the way. It only promises agreement at the end, after delivery is complete. Consistency is a destination the system arrives at, not a property it holds continuously. There's a quiet piece of history buried in this idea. The term eventual consistency was introduced by Doug Terry in 1995. He later remarked that he should have called it eventual convergence because the word consistency leads people to expect a shared present that the system was never designed to provide. The name itself encourages the exact misunderstanding that produces the bugs. If asynchronicity is the natural state, then the engineering problem changes shape. The goal is no longer to abolish lag. It is to detect lag honestly and to decide, deliberately, what to do while waiting to converge. The first move is to ingest rather than to ask. Instead of making a synchronous call across a service boundary, a service can consume every stream it depends on directly, pulling both inputs into its own bubble. In the well-known flower pot example, a builder service had to join a stream of flowers with a stream of preferred soil. Even when it was fully caught up on flowers, it returned not found errors for sunflowers and poppies because the soil stream, owned by a different domain, was lagging behind. The fix is not a synchronous lookup against the soil service. It is bringing both streams inside one boundary, so the join waits for both to arrive. The second move is to measure lag using offsets rather than event time. It is tempting to judge staleness by how long it has been since the last event arrived, but that measure lies on sparse streams. A compacted stream that only emits on change may sit silent for hours or days while its data stays perfectly valid. Comparing the latest available offset against the processed offset tells the truth that elapsed time cannot. The third move is to be honest about the bubble's edge. When a service knows its internal lag has crossed a threshold, it can say so, returning a stale data warning or a service unavailable response rather than answering from a view it knows is behind. And when a caller genuinely needs a value that has not converged yet, the service can offer a callback, letting the client register interest and be notified once the state has reached the required offset. What makes the time bubble worth holding on to is how much it quietly explains. The intermittent not found that vanishes on retry, the report that disagrees with the dashboard for a few seconds, the foreign key that exists everywhere except the one service that needs it. These stop being random misfortunes once you accept that every service is reasoning from its own position in a set of streams. There's a reassuring side to all of this. Most event-driven services are actually up to date most of the time. The anxiety that asynchronicity provokes tends to be larger than the frequency of the problems it causes. The streams catch up, the bubbles converge, and the system spends most of its life in quiet agreement. The shift that matters is one of expectation. A distributed system was never a single mind sharing a single present. It is a community of observers, each current as of a different point, each converging toward the others as the messages arrive. Once the universal now is set aside, the behavior that looked like chaos resolves into something orderly, and the bugs that looked like bad luck become things that can be measured, anticipated, and designed around.